Hello students, good morning and welcome to another video lecture of physics. After discussing all the MCQs, all the important concepts related to entrance exam, back to our normal lectures. In this video lecture, we are going to continue our discussion from our textbook. That is, we are going to discuss about Ampere's circuital law. So in this video lecture, we are going to discuss about Ampere's circuital law, and maybe if possible, we will discuss its application. So what is Ampere's circuital law? Look, Biot-Savart law is the basic law for obtaining magnetic field for any arbitrary shape conducting wires, right? Magnetic field produced by any kind of wire. On the other hand, Ampere's circuital law helps us to find the magnetic field in a quite simple way, right? Look, in one of the video lecture, we have derived the formula for magnetic field for a very long wire using Biot-Savart law. And you might have seen that in that case, we have to use all that trigonometric function and integration of sine and cosine and all that, right? But that is really a lengthier one, right? But Ampere's circuital law can be applied in certain cases where we have symmetric, like where we have infinite conducting wire, or let us say for solenoid, toroid, for all those kind of devices. Instead of Biot-Savart law, we can apply Ampere's circuital law to get the answer in a quite simple way, you can say, right? It is just similar to like Gauss law and Coulomb's law. You can obtain equation of electric field or force, right? Electric field by using Gauss law. But the same equation for electric field can be easily obtained by using Gauss law. If you are using Coulombian law to find the electric field produced by an infinite long wire, then it will take some time. The calculation will be quite lengthier one. On the other hand, in first chapter, you have obtained equation of electric field for a very long conducting wire, right? In fact, you have also discussed the cases for a hollow sphere and a solid sphere. You can easily find electric field by using Gauss theorem, right? In the same way, instead of using Biot-Savart law, we can use Ampere's circuital law to find the magnetic field in a quite simple way. Clear? So that is Ampere's circuital law. Advantages of Ampere's circuital law. So what is Ampere's circuital law? We'll write ACL, Ampere circuital law. Before starting Ampere's circuital law, okay, let us discuss Ampere's circuital law first. Suppose we have few current carrying wires. Let us say these are the few current carrying wires, and they are carrying current in random direction, any particular direction. Let us say this wire is carrying current I1 in upward direction, this is carrying current I2 in downward direction. Let us say again I3 in upward direction, I4, sorry, in upward direction. Let us say I4 is also in upward direction, I5 is in downward direction, and I6 in upward direction. Randomly you can select, right? So randomly we have selected some current carrying wires. Now look, while applying Gauss theorem, it is necessary to have a closed surface, right? And that was known as Gaussian surface. If you remember, you have called that surface as Gaussian surface, in which enclosed charges were there. So the concept was something like this. Suppose if you have charges, we are discussing about Gauss theorem or Gauss law, right? Suppose we have a closed surface, and this closed surface was given name as Gaussian surface, right? Let us say here we have charge Q1, Q4 and Q6. Here we have charge Q2 somewhere over Q3 and here Q5. So total we have 6 charges Q1 till Q6, right? So the Gauss theorem is something like that. Integration over a closed part, integration E dot dA over a closed part is sigma Q over epsilon naught. Sigma Q is algebraic sum of all the charges, but this sigma Q, these charges are which charge? These are enclosed charges, if you remember, and this electric field is due to all the charges. All the charges means from Q1 to Q6, and this is enclosed charge means only Q1, Q4 and Q6, right? This was the equation. This is surface integral. You have also come across line integration of electric field, integration E dot dl, right? That is work done and all that. So line integration of electric field across which you have come. In the same way, this is surface integration of electric field. This is our Gauss theorem, which is integration E dot dA is sigma q over epsilon naught, where sigma q is the enclosed charges, the charges which are present inside the closed surface, while the electric field which we should consider is due to all these charges, right? In the same way, here also we will require a closed surface. For Ampere's circuital law, we will require a closed surface, like what was necessary in case of Gauss theorem or Gauss law. So here let us consider a closed surface like this. Look, it is not necessary that the surface must be a circular, it can be of any arbitrary shape. In case of Ampere's circuital law, we require a current element, we require a small element. So let us select a small element in anti-clockwise direction. These are the small elements for this closed loop. We have selected these elements in anti-clockwise direction, right? Now for anti-clockwise direction, how to find the sign, right? In this case we have positive charge and negative charge. So here how to find the sign for current? Look, current is a scalar quantity, so obviously it will not have any sign, but actually the direction of current, to indicate the direction of current, we should have some sign. If current is moving in upward direction, if we can take that positive, then current moving in downward direction must be taken as negative. Or if current moving in downward direction is taken as positive, then current flowing in upward direction must be taken as negative, right? So how to decide which current is positive and which current is negative? So for that we should use right hand screw rule. We should use right hand screw rule. That is, if this is the surface, if let us say this is the Amperian loop, this closed surface is known as Amperian loop. This is Gaussian loop, this is Amperian loop, right? So let us say here we have an Amperian loop. What we have to do? We have to place a screw on this surface, right, and rotate this screw in the direction of these elements. Here you have taken elements in anti-clockwise direction, so rotate this screw in anti-clockwise direction. Place this screw on this loop, right, and rotate this screw, right, in anti-clockwise direction. So if you are rotating a screw in anti-clockwise direction, you will find that it is always coming out. If you want to fix that screw, it should be rotated in clockwise direction. If you rotate this screw in clockwise direction, it will move down, and if you rotate the screw in anti-clockwise direction, it will always come up, it will always move in upward direction. So here we have taken a loop in anti-clockwise direction. The elements of the loop are selected in anti-clockwise direction. So for anti-clockwise direction, the current which is moving in upward direction must be taken as positive, because screw will move in upward direction, right? While the current which are moving in downward direction must be taken as negative. Or in other words, suppose this is the Amperian loop, then you have to rotate your finger, or you have to bend your finger in the direction of these elements. You will find that thumb is pointing in upward direction, right? If you rotate your palm or your finger in, if you bend your finger in anti-clockwise direction, you will find that your thumb is pointing in upward direction. For clockwise direction, thumb will be pointing in downward direction. So here we have selected anti-clockwise direction. So current which are moving out, that is perpendicular to the plane and coming out, should be taken as positive, while the current which are entering inside the loop must be taken as negative. So here sigma I summation will be equal to I1 plus minus of I2 plus I3 plus I4, right? This will be sigma I. Why we have not considered I5 and I6? Because they are outside the closed loop. You can see here that here the sigma q, the summation of charges, are those charges which are present inside the closed loop. So in this case also, the current which we should consider sigma I must be those current which are enclosed by the closed loop, right? So here we have considered only up to I4, not I5 and I6, because they are outside the closed loop. Clear? This will be the algebraic sum of the total current enclosed by the closed loop. Now what is Ampere's circuital law? It is actually integration over a closed path B dot dl equal to mu naught sigma I. Mu naught sigma I. Look, always you should remember that in electric field the position of epsilon naught, and in magnetic field the position of mu naught are always reversed. In this case epsilon naught is in denominator, so in this case mu naught will be in numerator. If you remember, constant k is 1 over 4 pi epsilon naught. So epsilon naught was in denominator, right? Look, something like this was there. 1 over 4 pi epsilon naught is the constant for electric field. So 1 over 4 pi epsilon naught is in denominator, so mu naught was in numerator. This is constant for magnetic field, right? So mu naught and epsilon naught are generally in opposite places, right? One is in denominator, then another will be in numerator. Here charges are responsible for electric field, so sigma q upon epsilon naught. Here current is responsible for producing magnetic field. Current is responsible for producing magnetic field, so sigma I. And since here epsilon naught is in denominator, mu naught will be in numerator, so mu naught sigma I. Remember, this is the line integral. On the other hand, Gauss law is a surface integration, integration over a surface, integration E dot dA. Here line integration of electric field will give work and potential. All those things you have learned in chapter 2. We are not going to discuss right now. So this is the equation for Ampere circuital law, and if you write this in statement, that will give you the statement for Ampere circuital law. That is, this is the line integration. So the line integration or integral over a closed path. The line integral, line y, because dl is there. If it is dA, then the surface integration, but here length is there, so the line integral or integration over a closed path of magnetic field. The line integral of magnetic field, the line integral of magnetic field or magnetic induction, you can say, over a closed path is equal to the line integral of magnetic field over a closed path. The line integral of magnetic field over a closed path. The line, this is line, right? So line integral of magnetic field over a closed path is equal to the product of algebraic sum of total current, algebraic sum of the current, total current you can write, algebraic sum of the total current enclosed by closed loop. The algebraic sum of the total current enclosed by that closed loop and magnetic permeability, that is mu naught, of free space. If you want, you can write, right? So the line integral of magnetic field or magnetic induction over a closed loop is equal to the product of the line integral of magnetic field over a closed loop is equal to the product of algebraic sum of total current enclosed by that closed loop and mu naught. If you remember, this is the surface integration of electric field over a closed loop is equal to the ratio of the algebraic sum of the total charge enclosed by that closed loop to epsilon naught or n epsilon naught, ratio of Q, sigma q and epsilon naught. This is product of mu naught and sigma I, right? Here also you should remember that sigma I is the current only enclosed by that closed loop. Sigma I is that current which is enclosed by closed loop. The currents which are outside the closed loop must not be considered. As well as on the other hand, you can say that this magnetic field will be due to all the current carrying wires. This magnetic field will be due to all these current carrying wire. Like what is here, this electric field is due to all the charges, and on the other hand sigma q is only those enclosed charges, right? In the same way here magnetic field will be due to all the current carrying wires. The magnetic field which we should consider must be due to all the current carrying wires. On the other hand, sigma I is the current is only those current which are enclosed by the closed loop. Clear? Now here Ampere's circuital law for magnetic field, right, and Gauss theorem for electric field are the two important pillars of Maxwell theory of electromagnetic radiation. If you remember, in chapter 8 we have discussed something related to Maxwell theory of electromagnetic radiation. So out of four pillars of Maxwell theory of electromagnetic radiation, these two, that is Ampere's circuital law for magnetic field and Gauss theorem for electric field, are the two important pillars. The remaining two are magnetic field lines always form a closed loop. That was the third pillar for Maxwell theory of electromagnetic radiation, and the fourth one was displacement current. That topic is left, right, and that topic is based on Ampere's circuital law. So maybe in after few lectures we will discuss about displacement current, right? So the four pillars which are the most important pillars for electromagnetic theory, which was given by Maxwell, are Ampere's circuital law for magnetic field, Gauss theorem for electric field, magnetic field line always form a closed loop, and fourth one is the concept of displacement current. These were the four important pillars, right? One more important thing, Biot-Savart law and Ampere's circuital law. Ampere's circuital law is basically an integral form of Biot-Savart law. Ampere's circuital law is an integral form of Biot-Savart law, and Gauss law is an integral form of Coulomb's law. This can be asked in MCQ, right? In the form of MCQ, that Ampere's circuital law is an integral form of blank. Biot-Savart law, Coulombian law, then you may write universal law, Newton's universal law, right? Anything like that. So actually Ampere's circuital law is an integral form of Biot-Savart law, and Gauss theorem or Gauss law is an integral form of Coulomb's law. If you want, we can write here. Or do one thing, pause this video and all this point will write again on the board. So pause this video and copy this first. So here we can say that the first point is, which you have come across in chapter 1, Gauss law is an integral form of Coulomb's law. Gauss law is an integral form of Coulomb's law. Ampere's circuital law is an integral form of Biot-Savart law, right? The four important pillars of Maxwell's theory of electromagnetic radiation are the four important pillars of Maxwell's theory of electromagnetic radiations. There were the four important pillars, means he used these four concepts to obtain the theory of electromagnetic radiation. The first one was Gauss. It can be written as Gauss, or you can read it as Gauss. Actually it should be Gauss theorem or Gauss law for electric field. Why we have to write electric field? Because we do have Gauss theorem for magnetic field, right? Integration B dot dA is always 0. Okay. The second thing is, you must be doing it, right? Integration over a closed path B dot dA is always 0. Why 0? Because magnetic field, look, for case of electric field, integration E dot dA will be 0 if sigma is q is 0. That is for electric dipole. For electric dipole, sigma q is always 0. So you can say that integration E dot dA is equal to 0 for electric dipole. But magnets are always available in the form of dipole. Monopole of magnet is not possible, right? So they are always in dipole form. So this is always 0. Clear? Second one is Ampere's circuital law for magnetic field. You can write. If you will not write, then also Ampere has given circuital law only for magnetic field. Ampere's circuital law. Third point was magnetic field lines always forms a closed loop you must be knowing this, electric field lines never form a closed loop. They starts from positive charge and ends at negative charge. If we have a positive charge over here and a negative charge over here, then electric field will start from positive and ends at negative. Right, you can see that all the electric field lines will enter the negative charge and will come out from the positive charge. On the other hand, if we have a bar magnet, we have already discussed in chapter 5, this is north and this is south pole, then magnetic field lines emerges from north and enters the south for a bar magnet, right? We also discussed that actually the case is different. This is the case, right? Similar to what we have seen over here outside the magnet, but inside these field lines do travel from south to north to form a closed loop. So magnetic field lines always form a closed loop. And the fourth one is concept of displacement current. Concept of displacement current. These were the four pillars of Maxwell theory of electromagnetic radiation. Clear? So do one thing, pause this and copy this. These are all important points for your MCQs, right? Numbers of MCQ can be prepared based on this concept. So pause this video and copy this. So for some of the applications, we will find that Ampere's circuital law is the much simplified version to obtain the equation of magnetic field, right? You can say that Biot-Savart law is a complicated one, right? Its method and to derive the formula is much more complicated to find the equation for magnetic field. On the other hand, Ampere's circuital law is a simplified version, and you will find that it is quite easy for us to solve the or to obtain the equation for magnetic field in some of the applications. But for those applications, certain conditions are necessary. Then we can use Ampere's circuital law, right? Say for example, if we take a straight current carrying wire, if we have a straight current carrying wire, then we have to select an Amperian loop. Amperian loop must be selected in such a way, or we must be able to select an Ampere loop in such a way that, look, for this current carrying wire, let us say current is flowing in upward direction. So if we are selecting an Amperian loop like this, let us say we are going to take in anti-clockwise direction only. So if we select an Amperian loop in this direction, generally we are going to take in anti-clockwise direction. It will do. If you are taking in clockwise direction, our answer will not change at all, right? Then the Amperian loop must be selected in such a way that, number one, magnetic field B vector must be tangential. Magnetic field must be tangential to the loop. That is, magnetic field must be tangential to the loop, and it should be non-zero, and must be non-zero, right? So in this case, you can see that if this is the current carrying wire, right? If this is the wire which is carrying currents, and if you place a thumb in the direction of current, then your finger will be rotating around, or you will bend your finger in the direction of you can say anti-clockwise direction. You bend your finger in anti-clockwise direction. So for wire, magnetic field here, suppose if this is the wire towards you, then magnetic field will be in anti-clockwise direction, right? If current is flowing towards you. If we draw like this, if this is the wire, right, and it is towards you and current is also flowing towards you, then magnetic field will be circular around it, right? Magnetic field will be circular around it, right? So if we select this Amperian loop, then at a particular point, magnetic field line will always be tangential to the loop. If we select the same loop, then at any given point, magnetic field will always be tangential to the given loop. In this case also, the figure which we have drawn, at a particular point, let us say at this point, magnetic field will be tangential to the loop. Here also magnetic field will be tangential. At any particular point, magnetic field will be tangential to the loop. So we have to select an Amperian loop in such a way that magnetic field is always tangential to the loop, right? And it should be non-zero. The second one is, if magnetic field is not tangential, then magnetic field B must be perpendicular to the loop. Which loop? Amperian loop. Magnetic field must be perpendicular to the Amperian loop. It will make our calculation easier one, right? Here magnetic field is tangential to the current carrying wire, right? So magnetic field and Amperian loop both will be in same direction, so angle will be 0 and cos 0 will be 1. Actually our formula for Ampere circuital law is integration over a closed path B dot dl is sigma I into mu naught. So B dot dl is actually B dl cos, it is actually B dl cos theta, and it is equal to mu naught sigma I. So in this case, if the first is the case, right, in this case magnetic field and Amperian circuital loop both will be in same direction, right? For a straight current carrying wire, if you are selecting an Amperian loop circular form, in the circular form, then magnetic field is also circular. So both are in same direction, right? You can say, so in that case either theta will be 0, and if they are in opposite direction, anti-clockwise direction and clockwise direction, so in that case angle will be 180 degree. So you can easily simplify this, right? On the other hand, for this case angle will be 90 degree, so the whole term will become 0. Clear? And the third one, B, that is magnetic field vanishes, that is it quickly becomes 0 and completely disappears. You can say magnetic field should completely disappear suddenly, right? So magnetic field must vanish. So these are the 3 points we should keep in mind while selecting Amperian circuital loop. Remember, in most of the cases this thing we are going to select, so no need to worry about the remaining 2 points, right? We are going to discuss, or in our chapter the concepts are related to this only. We are going to select an Amperian loop in such a way that it is always tangential to the magnetic field. Clear? Or magnetic field is always tangential to the loop. Fine. So in next video lecture we are going to discuss about the applications of Ampere circuital law. Look, we have I think 3 applications based on Ampere circuital law, like what you were having for Gauss theorem. For infinitely long wire, positively charged linear wire, you have find electric field, then hollow sphere and solid sphere. Even you have discussed electric field for a infinitely long thin sheet, right, charged plane, you can say. In the same way, we have 3 applications of Ampere circuital law, or you can find magnetic field for 3 different types of devices. One is a very long current carrying wire, the another one is solenoid, and the third one is toroid. So those 3 applications will require 1 lecture for each. So in next 3 video lectures we are going to discuss 3 applications of Ampere circuital law. One is for infinitely long current carrying wire, both inside and outside. Then we will discuss about solenoid and then toroid. Clear? So this is it for this video lecture. Hope almost all the concepts are clear. Thank you.